Okay, this was what I wanted to tell you about the group code. Yes, I created another group for Jan. So, like I was telling Iram just now, that I'm uploading all the 10 years papers after going back today in that. At the same time, any content that I find based on the chapters that we will be covering routinely, I'll put it up over there. Well, I can do it either ways. You want me to put up all the papers together, I can do that. Or else, say for example, if we do acidity basicity today or any topic, then I can pull out questions only pertaining to the topic that we've covered from all these 10 years, and we can discuss them at one shot, and then we can move on. We'll do acids basis today. Okay? Yeah, so we'll take it as we go through, connect to this thing, then eventually we'll fine tune as to how exactly to go about it. Okay? There are 3 books that I have found content to be very good on acids and bases, out of which one of the book happens to be quite a favorite in terms of the questions asked. If you pull out the previous year's papers on acidity and basicity, you will see that majority of the questions as it is have been picked up from Claydon. As it is. Yeah. As it is have been picked up from Claydon. Of course, Claydon is a book that we don't recommend to people who are beginning with chemistry. We ask our postgrad students to refer to Claydon, because Claydon happens to be a Bible by the time they come into their PGs. So for organic chemistry, it is Claydon and March that we go to for whatever. Yeah, Jerry March and Claydon is what we go to for any concept in organic chemistry, right? Now, even though acidity and basicity has not been like in detail, this is what I was explaining to her, that it's not been mentioned in detail in the syllabus. That also reminds me that I'll put up one PDF file on the syllabus, on the latest syllabus as well of Jan that is required of you. Okay? Just to discuss briefly the paper pattern as it was in 2015 and now it's going to be. There are 3 types of questions. The first section is going to involve MCQs, okay? And this section of MCQs has had 2 different weightages, in the sense that all the questions don't have the same number of marks. Please be very, very aware of what is the marking scheme, because as you have +1, you have -1/3 for the negative answer over here in the first slot, and you may have few questions which are 2-mark questions in MCQ. So where the weightage of the question is 2 marks, the negative marking also becomes -2/3. So even though when you get it right, you get more credit for it. If you go wrong in those questions, you lose more credit as well. So you need to be very aware as to how the marking pattern is for this section, right? Then there is a second section called as MSQ, which is called as multiple select question. There is negative marking in MCQ, -1/3. There is no negative marking in MSQ, but at the same time there are no partial credits that are offered for MSQ. What do you mean by partial credit? Say for example, 2 out of 4 answers were the correct answers for that particular question. You mark out any one of them that is correct, but you don't get half of the marks allotted for that question. You don't get any marks at all, even though there aren't any negative marking. So there is no partial credit in this particular section. That is what increases the complexity here.
In the MSQ section, the actual probability of not getting a complete mark is very less, because the options in the answers have been set in such a manner that it's obvious it's going to. Are you understanding what I'm trying to say? Then
not necessarily. Actually, in fact, in the last year's MSQ was not there in the years before last. Last year was the first time when they introduced MSQ. Now, if you remember, Iram, you had this chapter on phenols last year. You had routes of synthesis of phenols, right? There were 4 of them: Dow's process and through benzyne, or there were 4 different cumene hydroperoxide method, or such. There were 4 reactions which were given last year. I'm talking about this last year's paper. So they had given each of those 4, and they had the title of the question was, through which process can you prepare phenol? All 4 of them were the correct answers. Okay, and the student who answered the paper, I mean, you get almost a printout of your paper along with your own options as well. You can save it as a PDF and you can mail it back to yourself from the internet center where you are appearing for the exam. So over there she had marked 3 because she remembered 3 at that time. I mean, to be fair to her, 3 out of 4 is not bad, right? I mean, you remember at least 3 of them definitely are routes of synthesis of phenols. No credit was given to that because all 4 of them gives phenol at the end. She didn't recognize the cumene hydroperoxide. Dow's benzene and one more reaction was relatively easy to identify in that particular sequence. Cumene hydroperoxide is slightly off, right? You have cumene along with oxygen, so it's really far-fetched to understand that, okay, fine, cumene with oxygen in the presence of a catalyst can also give phenol and acetone as a byproduct, but it's one of the most important industrial route of synthesis. So no credit, no partial credit was offered to that. So it's like, some questions you may feel that 2 options are very close together and they are obvious, but in such kind of questions when you have 4 different routes all leading to the same product, sometimes it becomes difficult to score your credits in MSQ. Okay? And the last section is called as NAT, which is called numerical answer type questions, wherein there will be no options at all. There will only be a box where you can key in your answer, and those the answers should only be numeric basically. So you can only enter numeric entries inside those boxes to the nearest whatever that they specify, that it should be to the nearest ones place or nearest first decimal place or to the nearest second decimal place and so on and so forth. So whatever answer you get, you're supposed to key in over there. Calculators are not allowed, your own calculators are not allowed, but on this machine which you are working the test on, you can conjure a calculator that is present and you can use the calculator of the machine, though calculators are not allowed to be carried inside the examination. It will not have too complicated calculations, but at the same time you need to know the formulae and how exactly to go about it. Majority of the problems there I have seen are based on electrochemistry, because electrochemistry has a fair bit of calculations. Whether you talk about if I pass electricity for so much length of time, what should be the weight of. So all the constants they definitely provided to you. They provide the value of a Faraday, they provide you almost everything. But the only thing is you will have to ultimately arrive at your final answer, which will be a numerical value. Or sometimes calculation of pKs, pKbs, etc. All those things can also come.
Provide the periodic table?
Yeah, they do. Yeah. You don't need your atomic weights or atomic numbers. That is always given to you. In fact, earlier when we used to have paper-based exams, the first page used to be the periodic table and the constants used to follow. Only below the constants they used to start. When I upload the PDF files, you will come to realize that as you go through the PDF files, you will see that right in the beginning you have all your constants and below that only you start with these questions. Okay. So like I was saying, that the acidity and basicity has not been explicitly mentioned in your syllabus, but as soon as you look at organic chemistry, it says hyperconjugation, resonance, inductive effect and its applications. And just into a small bracket it says acidity, basicity of organic compounds. Because in most cases acidity and basicity can be explained based on one of these effects basically. Right? So we'll just broadly go through acidity and basicity, and then I'll try and condense the matter in these 3 books which are totally standard for organic chemistry. I'll try and see if I can scan it through, then I'll put it up on Edmodo. You can take it out and you can go through it wherever you are and try to solve the questions. Okay? These chapters also contain questions behind them. So it will be a good practice as soon as and when we go, we should pull out the questions from behind these standard books also and try to solve them. Because like I said, when you go through your questions, majority of the questions have been picked out directly as from the examples or from the end of the chapters from these standard books itself, right? So, okay, in this particular chapter, we need to be able to understand the strength of different acids, how strong or how weak. Okay. Now for that we need something to compare with, right? So we need to get used to some quantities called as Ka and pKa, Kb and pKb. Right? Remember that there are 2 Ks in chemistry. One of them is a capital K and the other one is a small k. the capital K has to do with thermodynamics and the small k has to do with kinetics. Now remember that these two things are quite mutually exclusive when it comes to chemistry. Okay? Therefore, when you start doing your chemistry, a little more advanced chemistry, you will come across something called as thermodynamic control and kinetic control. So you do reactions under kinetic control or you can do reactions under thermodynamic control. Okay? The small k only tells you how fast or how slow the reaction is happening. Okay? The capital K tells you what should be the equilibrium constant for a reaction happening. Okay? So all these constants are basically equilibrium constants, which are basically the ones resulting from dissociation of either an acid or a base. Therefore, we call them as Kas and Kbs.
You asked him what I told you. I said I'll give you 5-star Cadbury, chocolate, silk, smooth, whatever, but don't come for my education.
And today I was the least active.
Yeah.
He doesn't understand English. So I have given him the SYBC textbook from Sir. I don't have his contact number. So Monday, just please send him a reminder to return.
Sure.
He doesn't, I don't know financially also how, because he doesn't want to buy from outside. So I've given it to him.
Okay. Okay, so these K's, remember, are the capital K's which stand for the equilibrium constants. Okay, and when I say Ka, it is the equilibrium constant for the dissociation of an acid. Okay, before we move completely to organic chemistry and try to understand which organic acid should be stronger, which one should be weaker, we need to have some physical background of what these parameters are and how they are obtained, right? Now, an acid dissociation can be simply represented as Ha dissociating to give you H plus and A minus, right? Now, for an organic chemist, this equation is okay. There's no problem with this equation. But a physical chemist will not be very happy with this equation. A physical chemist will be happier if I wrote Ha plus H2O. You cannot have free proton in solution. You will always have hydrated proton. Okay. So whenever we are looking at loss or gain of proton, it cannot happen in isolation. If something is losing a proton, there should be something else to gain that particular proton and become some other species, right? So if you generate a species which you are very well aware of, which is called as the hydronium ion, and you will generate the same A as A minus, right? Now the concept that there are three concepts of acids and bases. Which are they? Which is the first concept of, Arrhenius is the very first concept of acid and base. The next one, Bronsted-Lowry, and the third one, Lewis acids and bases, right? Now the concept that we will be using more often will be the Bronsted-Lowry concept to understand what is the acidity and the basicity. Okay? As it goes, you will come to realize that there will be more so derivation and application of the Bronsted-Lowry concept as against the other two. Okay? Now, if I want to write the equilibrium expression of this equation, now try to get used to your equilibrium expression also, because you have at length Ka, Kb, Kh, Kw, and all the K's possible. Okay, but in a sense, any K can just be written as product of concentration of the products divided by product of concentration of the reactants. Okay, and in chemistry, concentration of, the term concentration of is just written as species enclosed in square brackets, right? So if I want to write the equilibrium constant K for this equation, I just take K is equal to H3O plus multiplied by A minus divided by HA multiplied by H2O. Now we will send it to the constant K. Okay? Now why exactly the concentration of H2O does not change? Let us assume that whenever we are mixing an acid with water, I usually deal with solutions which are like 0.1 normal, 0.02 normal, 0.025 normal, and so on and so forth, right? So our solute, which is basically our acid, is much less in quantity as compared to water, which acts like the solvent. In fact, by definition, solvent is the one that is going to be present in a larger quantity as compared to the solute, right? So my solvent being so many in number, let me put a hypothetical value that there are 10,000 molecules of water, okay? And if there are 10 molecules of the acid, even if the 10 molecules of acid are completely dissociated, only 10 out of 10,000 molecules of water will exist as H3O+. Can you note that? So 10 out of 10,000 is a very, very small quantity. So you will still have 9,990 molecules of water, which is as good as the initial concentration of water itself. That's why we say that the water's concentration appreciably does not change and remains a constant. What I cannot send on the left hand side are species which are variables. What I can very reasonably send to the left hand side are species whose chemical composition remains fixed or whose concentration remains unvaried throughout the reaction. Now, why is our assumption that the concentration of water does not change is that because it is present in such a large excess, its concentration will not appreciably change over gaining few protons from the acid, which is present in much lesser quantity. And therefore, if I can send this over here, assuming it is a constant multiplied by a constant will generate a new constant, right? And that constant is what I term as Ka. So when you write Ka, the term Ka already has the concentration of water, that term, incorporated in it. So I do not need to write Ka is equal to H3O plus multiplied by A minus divided by water and Ha. I can just write Ka is equal to H3O plus multiplied by A minus divided by Ha. Right? So that becomes my value Ka. Higher the value of Ka is, more acidic my compound is. That is the straightforward relationship. Ka is nothing but the dissociation constant. More dissociated the acid is, more stronger it is. Right? Now since Kas in organic chemistry usually are of the order 10 to the power minus 5, benzoic acid has a Ka which is approximately around this much. Okay. Phenols have Kas in the approximate range of 10 to the power minus 10. Okay. So you see that the Ka values are very, very low. Organic acids are generally weak acids as compared to inorganic acids. Inorganic acids, HNO3, H2SO4, HCl are much stronger acids, right? Whereas organic acids are weak acids, and therefore these values are not very easy to handle, right? To instantly say whether 10 to the power minus 5, 10 to the power minus 10, 10 to the power minus 6, etc., how do they compare with one another is relatively difficult. Okay, so I do some mathematical treatment on this Ka, and the function P is added in front of Ka. This P is nothing but a mathematical function which stands for negative log of, and especially negative log to the base 10 of. Okay, so you could have you do something called as MIC in your minimum inhibitory concentrations in your biological sciences, right? Now since minimal inhibitory concentrations are also values which are extremely small, you can't have minimal inhibitory concentration of 2 kgs of the compound in your body. You'll die taking 2 kgs of the antibiotic, right? So the minimal inhibitory concentrations are extremely small, in few micrograms or few milligrams and so on and so forth, per body weight or whatever. And therefore in papers, you see research papers usually plot a value called PMIC. What does PMIC indicate? P is a mathematical function, and that mathematical function is being operated on a value, that is MIC. You get values which are much more easy to handle. Now you no longer have 10 to the power minus 3 of a gram, 10 to the power minus 5 of a gram, and so on and so forth. You will have values like, if I operate a negative logarithm to this value, I get a value 5, which is much easier to handle. If I take the negative logarithm of this, I get a value 10, which is much more easier to handle. Okay. Now how exactly does the acidity Ka and pKa compare with one another? Higher the Ka, more is the acidity, but higher the Ka, lower is the pKa. Okay, so there is an inverse relationship between Ka and pKa. Higher the Ka, lower is the pKa, and obviously the other way around. Lower the Ka, higher is the pKa going to be. Okay, so you should be able to readily identify whether you have to account for high acidity, low acidity, etc. For that you need to be comfortable with these notations. If I say for example, I give you two compounds. Phenol, I say, has a pKa value of 10, and I give you a compound called paranitrophenol, which has a pKa value of 7.35. To account for the acidity order, you will first need to know which one is more acidic and which one is less acidic. That means you need to process these experimental values. Okay, this is my favorite thing which I keep saying in every class, that not because we are saying something should it happen in the lab. What comes first? The experimental observation comes first. Okay, what do we measure? We measure the pKa values in the lab. pKa values can be very easily measured in the lab. We just need to know the concentrations, right? We are just given the expression. If I know the concentration of H plus and A minus in solution, I can calculate the Ka value. In fact, in SYBSE you will have one practical of using a conductometer or a pH meter to verify the Henderson's equation, or using the Henderson's equation to judge the Ka value of some acid. That is also possible. All these things are experimentally determined values. Okay, so once the experimentally determined values are given to you, you as organic chemists need to account for the value of acidity. Okay, so for that we will need to know whether pKa of 10 accounts for higher acidity or pKa of 7.35 accounts for higher acidity. So how does it compare? Higher the value of pKa, lower is the value of Ka, and lower is the acidity, right? So which of the two is more acidic? Paranitrophenol is more acidic as compared to phenol itself. Then we start thinking, okay, which effects are going to operate to make paranitrophenol more acidic as compared to phenol, and we can start giving some reasons and explanations based on the mesomeric effect, the resonance, and so on and so on, right? In fact, there is a compound what is the name of this compound? This is picric acid, right? When I say acid in organic chemistry, which functional group strikes your head? Anything else? Anything else apart from COOH? Carboxylic acid, and there's only one, sulfonic acid. So COOH and SO3H, both of them are acidic functional groups in organic chemistry. Doesn't contain either of them, but still we call it as an acid. Why? Because the pKa value of picric acid falls in the range of approximately 2. For benzoic acid, I said the pKa value was approximately 5. That means this phenol is even more acidic than benzoic acid is. By what factor? What, 3 times? 10 to the power 3 times. That means it is 1000 times more acidic as compared to benzoic acid. Remember that just like change in 1 pH unit indicates 10 times increase or decrease in H plus, similarly the increase or decrease by 1 pKa unit indicates 10 times more acidic or 10 times less acidic. Okay, so since there is a difference in about 3 pKa units, there is 10 to the power 3 times difference in acidity. So 10 to the power 3 is nothing but 1000. So 1000 times more acidic than benzoic acid.
What are you comparing?
Benzoic acid with picric acid.
So benzoic acid has a pKa value of
5. Yeah, approximately 5. Substituted acids will have some slight variation. We'll see how substitution actually changes the pKa values of these acids, right? So to understand or to be able to account for acidity, we need to understand these values first. That's why I want you to be comfortable with pKas as well as with Kas and Kbs, right? If I give you aniline, methylamine, trimethylamine, and so on and so forth. These are all organic bases. But in books, you can see either pKa values written for these compounds, or you could see pKb values for these compounds. Okay? That is what I want you to appreciate, because how do you interpret the results if pKa values are given, and what do those pKa means? Because pKa means an acid dissociation constant. Now, since there is no acidic functional group here, how do you interpret the pKa or the Ka for such kind of compounds? For a conjugate acid-base pair, that relationship holds, and that is what we need to understand very, very clearly, that if at all I talk about a conjugate acid and a base pair, what do you mean by a conjugate acid and a base pair? A conjugate acid and a base pair only differs by a proton. So when you have Ha and it gives you A minus by liberating a proton, the Ha and A minus pair is called as a conjugate acid-base pair. Okay, where Ha will be called as the acid. Why should it be called as the acid? Because according to the Lowry-Bronsted theory, it is acting as a proton donor. Proton donors, according to Lowry-Bronsted theory, are classified as acids. And A minus over here acts as a proton acceptor, and therefore we call it as the conjugate base. Right? So we call this as a conjugate acid-base pair. Okay? Now, for a conjugate acid-base pair, there is a simple relationship which says that Ka multiplied by Kb should be equal to Kw. Ka multiplied by Kb should be Kw. If I take negative log throughout this equation, I will get negative logarithm of Ka, negative logarithm Kb is equal to negative logarithm of Kw. Because in logs, we don't have multiplication in logs become addition and division. But I am taking the negative log of. I am not taking the normal log. If I take the normal log, it will be positive. But if I take normal log, I can't substitute it for p. My intention is that it should start looking like p, basically, the function p, and the function p is negative logarithm of. So I take the negative log on both the sides. So I get this equation, and now I replace this negative log by p, and I get pKa plus pKb should be equal to pKw. Okay? Where pKw is nothing but the negative logarithm of the ionization constant of water, and usually we take that at 25 degrees Celsius to be 10 to the power minus 14. In fact, that is why your pH scales range from 0 to 14, because the dissociation constant of water happens to be 1 into 10 to the power minus 14, right? And the negative logarithm of 1 into 10 to the power minus 14 works up to 14. You do pH plus POH is equal to 14 similarly, because the negative logarithm of concentration of H plus negative logarithm of concentration of OH minus should give you the dissociation constant of water, which is 14, right? So for the same reasons, you will have this relationship of pKa plus pKb also equal to pKw. But remember that this holds only for a conjugate acid-base pair. If I ask you to find out a quantity based on giving you the pKa, say for example, of sulfuric acid and of the sulfate anion, and I ask you to find out the pKb of the sulfate anion, it's not possible. Because the conjugate acid-base pair will be sulfuric acid with bisulfate anion, H2SO4 and HSO4 minus, and there will be a conjugate acid-base pair of HSO4 minus with SO42 minus. Only one proton difference should be there between a conjugate acid-base pair. Is that clear? So based on whether I give the pKa values or pKb values, you could still account for acidity and basicity order in these compounds, right? Okay. Now we need to account. We already know how to identify which one will be more acidic, which one will be less acidic. In case of acids, we follow a different pathway. In case of bases, we follow a different line of thought. Okay, what is the line of thought in an acid? For an acid, any organic acid Ha will dissociate to give me A minus, which is called as the conjugate base. We've already defined that based on the Cronstedt-Lowry theory. Okay. The line of thought is that any factor or any parameter that increases the stability of the conjugate base will increase the acidity of HA. When A minus becomes more stable, the reaction according to Le Chatelier's principle will be driven more and more towards the right, and hence the acid will tend to be a stronger acid. Okay? Whereas any factor that destabilizes the conjugate base is going to decrease the acidity. The reaction will start moving more and more towards the left hand side. Is that clear? So that is the line of thought in case of acids. What is the line of thought in case of bases? No, it's not the conjugate acid. If it was the conjugate acid, then we were moving across the same line of thought. In case of a base, we don't look at the conjugated acid. That's the difference. In case of an acid, if you want to judge the acidity, what do you look at? You always look at the conjugate base. We never look at the acid to understand the acidity of an organic compound. We always look or account for any stabilizing parameter or any stabilizing factor on the conjugate base. In case of a base, we move quickly to the Lewis theory. What is the Lewis theory of the base state? Electron donors. Electron donors are bases and electron acceptors are acids, right? Now, if a base has greater tendency of donation of electrons, it will be a stronger base. Whereas if the base does not have the electrons on itself to give away, it will be a weak base. So what do we look at for basicity? We look at electron availability. Whether the electrons are available or are not available. If the electrons are available to be given to a proton or to any other species, to a Lewis acid, then the base will be a strong base. If the electrons are not available on that particular species to be given, it will be a weak base. So that is how the line of thought is slightly different between accounting for acidity and accounting for basicity, or the order of basicity. Is that clear? Could have methane dissociating to give the methyl carbon ion and to give you a proton, right? Now in this case I am assuming that methane is acting as an acid because it is donating the proton and it is becoming a conjugate base which is like methyl carbon ion, right? Now when it comes to your questions will always be comparative. Nobody will ask you the absolute value of acidity of methane. Nobody is interested in knowing whether you remember the pKa value of methane or not. But if I give you an equation like this and give you another compound which is methanol, okay? Methanol dissociates to give you the methoxide anion and will give me H+. Again, I am accounting for the acidic property in methanol. Now, which of the two should be a stronger acid? Should methane be a stronger acid or should methanol be a stronger acid? Methanol should be a stronger acid. Okay, the first factor is that, what do we look at? Now, since we are accounting for acidity, we look at the conjugate base. Which are the conjugate bases here? The first conjugate base over here is a carbon ion. The second conjugate base over here is a methanol will be a stronger acid as compared to methane. Why? Because who is carrying the negative charge? So the first thing that you look at is who is bearing the negative charge. Okay? The negative charge is being borne, if it is being borne by a more electronegative element, then it is going to assimilate the negative charge much better than when a less electronegative element bears it. In one of the JAM questions, they had asked the same question in okay, so you've made a note of nucleophilicity and basicity. Now, what exactly is the difference between nucleophilicity and basicity? Basicity tells you how strong a base it is or how weak a base it is. Nucleophilicity depends on how effectively it goes and attacks an electrophile. Again, the concept is the same, because when you're looking at basicity, you're again looking at whether the electrons are available for donation or not. When you're looking at nucleophilicity, again you're looking at whether the electrons on this nucleophile can go and attack an electrophile or not. But what is the thin line of difference between basicity and nucleophilicity? Basicity is a thermodynamic concept. That's why you look at capital K's. You never look at small k. You're not bothered about whether the proton comes very, very slowly to the base or whether the base goes rapidly to the proton. You're only dealing with the thermodynamic equilibrium constants when it comes to basicity. Okay? Whereas in case of nucleophilicity, you are discussing a kinetic concept. A better nucleophile will necessarily not be a good base. You understand that?
So, but I feel all nucleophiles are bases.
All nucleophiles are bases.
All bases are not nucleophiles.
All bases are also nucleophiles, but at the same time, a strong base need not be a strong nucleophile, and a weak base will not be a weak nucleophile. That is what this means.
May or may not hold a negative charge.
Yeah.
Something like ammonia doesn't hold a negative charge,
Yeah.
but it is still considered to be a nucleophile.
Yeah.
But the exactly now okay, so it may not be a strong base as well.
Why not? Because basicity is a thermodynamic concept. In case of basicity, what do I just deal with? Product of the concentrations divided by product of the concentrations. I don't consider that whether that particular concentration of the conjugate acid is formed in 20 days or in 2 seconds. Am I considering that? No. But when I'm talking about reactivity and SN reaction, I will judge the rate of the reaction, and I will judge the nucleophilicity depending upon the rate of the reaction. A better nucleophile will be the one that will be able to give me an SN reaction at a faster rate. It may be an extremely strong base, but if it achieves that level of equilibrium constant after 20 days, its rate is extremely small, right? So it happens to be a weak nucleophile according to my standards. So whenever I am talking about nucleophilicity, I am talking about a kinetic concept, whereas when I talk about basicity, I am talking essentially about a thermodynamic concept.
So, but if it's a strong base, then it has to be a good nucleophile.
No, not necessarily. I'll give you an example. There are some compounds which are called as proton sponges. Okay, what do you mean by a proton sponge? Once the proton it's like a sponge that once it comes, everything goes inside. You can't get it out. This happens to be a remarkably strong base for what looks like quite a weak base. Why? Because there is a lot of steric crowding. The lone pair does not seem to be available to the proton, but as soon as you draw its conjugate acid, that conjugate acid happens to have a structure like this. I'm just drawing an enlarged view of this much. You get the proton coming here and a positive charge developing on this nitrogen, and it also forms a dotted line. You call that as the hydrogen bond, right? Initially, when the hydrogen bond was absent, you saw that the two lone pairs of electrons on the two nitrogen are present very close to one another. Is that a favorable situation? Lone pairs require a lot of space. So there will be a lot of lone pair repulsion. So even though the proton comes very, very slowly to this particular species, once it goes, it's very difficult to remove the proton from that conjugate acid. You understand? So you realize that the basicity of this compound is extremely high, because what are we measuring when we are measuring basicity? We are measuring concentration of this species multiplied by something else divided by concentration of this species. So at infinite time, once the equilibrium has been established, remember we never measure equilibrium constants before the equilibrium is actually established. You can't, measure the equilibrium constant as soon as the reaction started. You have to let it equilibrate, right? Only then you can measure the quantity called as equilibrium constant. So at equilibrium constant, naturally the concentration of this species is going to be tremendously high and the concentration of this species is going to be low. But having said that, the transfer of the proton is going to be very, very slow. We call such kind of compounds as proton sponges, and substituents on 1 and 8 positions of naphthalene, we call them as 1,8 position. They are also called as peripositions due to their very, very special interaction, steric interaction. We call them as peripositions. 1, 2, 3, 4, 5, 6, 7 and 8. So the 1 and 8 positions are called as peripositions, and there are some unfavorable interactions of the 1,8 position. Approach of the proton is slow, but once the proton comes in, it's very difficult to remove the proton because of such kind of favorable interaction, hydrogen bonded interaction between. Yeah, so the positive charge is stabilizing the repulsion between the two lone pairs. Because the proton should find some space also, right? There is a methyl here, there is a bulky methyl here, there are methyls everywhere. So the approach of the proton cannot be very fast or rapid towards the nitrogen. Yeah, with the lone pair, is it available? Is it free? Absolutely free? No, it has the naphthalene ring from underneath, so the proton cannot approach from underneath. It has 2 methyl groups here, 2 methyl groups there. So the approach of the proton is going to be restricted due to steric reasons, and therefore the approach of the proton is slow.
And when it enters,
once it goes, it's not going to leave the system. Therefore, your kinetics and thermodynamics cannot always be thought of to go hand in hand. So you can never assume that a good base or a strong base will be a strong nucleophile. There could be a change in the order, because basicity is a thermodynamic concept, nucleophilicity is a kinetic concept. Nucleophilicity only depends on how fast and how slow. So this compound should, according to you, be a strong base. Strong base, why? Because the concentration at equilibrium of this species is extremely high, but at the same time, since the approach of the proton is relatively very slow, it's a weak nucleophile. Did you understand that? Weak nucleophile because of kinetics, strong base because of the thermodynamics that it exhibits. Okay. Okay. So one is that we need to look at the atom which is bearing the negative charge to understand the stability, right? Another thing is, say for example, if two atoms, you have two different compounds in which the negative charge is being borne by the same atom. In this example, you have methanol, which is giving away a proton, becoming methoxide. Negative charge is again on oxygen. You have acetic acid, which is giving away a proton, becoming an acetate anion, right? Now the negative charge is on oxygen, so you can't invoke that explanation to account for acidity, because according to that explanation, both should be equally acidic. But which one is more acidic? Acetic acid is more acidic than methanol. So how do you account for this?
Resonance.
Exactly. Any factor that stabilizes the conjugate base increases the acidity of the acid, right? And what is stabilizing the conjugate base? The negative charge now in this structure no longer rests on only one atom. Okay? You have CH3C double bond O. You have double bond, single bond, double bond, and that leads to conjugation. Any conjugated system can have resonance, and that resonance is going to help in sharing this negative charge between the two oxygen atoms. And you draw a resonance hybrid indicating that the true picture of the molecule is neither like type 1 nor is it like type 2, but it is somewhat intermediate between type 1 and type 2, wherein you draw a dotted line and say that the negative charge is delocalized between the two oxygen atoms. This is the stabilizing phenomena for the conjugate base of acetic acid, making acetic acid itself more acidic as compared to methanol. So much so that in the lab, if you take litmus paper and do all the tests with methanol, ethanol, they'll test as neutral compounds. You've done that in organic spotting in your FI as well, right? Methanol, ethanol, all these alcohols test neutral. Whether you do the bicarbonate test, NaOH test, HCl test, after all these tests, they'll come to neutral molecules. Whereas acetic acid, you take acetic acid and dip a blue litmus paper, it is going to immediately turn red. It is going to test acidic in aqueous solution. Remember that those acids which have their pKa less than 14 act as acids in aqueous solution. Okay? For methanol and ethanol, the pKa value is just over 14. For methanol, it comes to about 16, 15, 16. For ethanol, it goes to about 17. Why should between ethanol and methanol, which one should be more acidic? Can you judge? If I tell you that here the pKa value is about 16, here the pKa value is about 16, which one is more acidic? Methanol is more acidic as compared to ethanol. Why is that?
Because of the extra carbonate is also having a positive.
The alkyl group is pushing electrons towards the oxygen due to its plus I effect. Okay. Now this alkyl group, if it pushes the electrons on the conjugate base, already oxygen has a negative charge. Any factor that reduces negative charge will be stabilizing. Any factor that increases the negative charge will be destabilizing. Okay. So in methanol, it will not be as destabilized because CH3 is a plus I group, but more than CH3, C2H5 will push the electrons more inductively towards the oxygen, and hence it will destabilize the conjugate base further. And therefore you see that ethanol is less acidic as compared to methanol, right? So both of them don't test as acids in aqueous solution at all. Why not? Because their pKa values are higher than the dissociation constant of water itself, which is Kw. We should take a solvent whose dissociation constant is higher than this. So we call such kind of chemistry as non-aqueous chemistry, okay, or non-aqueous solvents. So we do have such kind of, see, always remember that there is something called as a leveling effect of solvents. In water, the strongest acid that can exist in water is H+. But H+ is not the strongest acid possible. You have antimony hexafluoride called SbF6 minus, HSbF6. That compound is called as a superacid. Must have heard of it. HSbF6 is the strongest acid known. Does not exist in water. If you take HSbF6 and dissolve it in water, then it is going to level it to the strongest acid possible in water, that is H+. Do you understand that? NaOH, KOH, all these are strong bases, but they are not the only strong bases. We have much more stronger bases than them, like hydride, lithium aluminium hydride, sodium borohydride. These are extremely strong bases, BH4 minus or LiAlH4 minus. These are extremely strong bases. But at the same time, if you take lithium aluminium hydride and put it in water, the base level of hydride is going to be brought down to OH minus. So you call that as the leveling effect of solvents. So certain solvents can be differentiating, certain solvents can be leveling in their effect. Like if I ask you which one is the strongest acid, HCl, HNO3 or H2SO4, H2SO4 is the strongest acid. It is the king of all acids. But when the experimentation is done in an aqueous solution, I don't give you any non-aqueous solvent. I want to take some revenge on you. I ask you to go to the lab and do whatever experimentation you can, but tell me between HCl, HNO3 and H2SO4 which is the strongest acid, and I give you only water. You will not be able to find it. Because water acts as a leveling solvent for each of these acids. In water, each of these acids are going to test equally acidic. Okay? So you need some non-aqueous solvent to be able to differentiate these acids based on their acidity level. Not really. The most of the Ka values, pKa values that you get are basically non-aqueous values only.
Isn't
No, Arrhenius theory is based on aqueous solution.
Yeah.
Not Bronsted. No, not Bronsted. Bronsted only deals with proton donation and proton acceptance. It could be to a non-aqueous solvent, or it could be to water. If it is to water, then you are talking about aqueous acid-base chemistry. If you are talking about donation of proton to a non-aqueous solvent, then you are talking about a non-aqueous chemistry. Okay. Another thing that you must remember is acidic solvents act as differentiating solvent for acids. Okay, what do I mean by that? Say for example, I take acetic acid. Okay, in acetic acid, I take H2SO4, HCl, HNO3, etc. I'll get some pattern of difference in acidity, because acetic acid itself is an acid. So it is not going to very easily take up a proton. Do you understand that? Because it's itself an acid, it has a tendency of donation of proton, does not have a tendency of accepting a proton. So now an acid which is really strong will enforce the proton on acetic acid. But the acid which is not very strong will not be able to push its electron on. So therefore acids will act as differentiating solvents for acids. But if you take different bases in an acid, all bases will look equally basic in the acid. Why? Because it will level if I am a weak base, she is a strong base. My proton accepting capacity is not so much, but that is with respect to water, right? But if there is a person who's enforcing his proton on me, the proton is going to come to me as well, proton is going to go to her as well. So the difference between our basicity will be lost in a solvent which is pushing protons towards us. Are you understanding that? So acids become differentiating solvents for acids, whereas they become leveling solvents for bases. So all your ammonia, methylamine, ethylamine will all test equally basic in an acidic solvent like perchloric acid, acetic acid, etc. Okay? Whereas in water you can differentiate them. Or else if you want to differentiate further, say for example, then you take a basic solvent. Then what is going to happen? The base also is going to compete for taking up the proton, and hence there is going to be greater differentiation in the base strength of the bases. Okay, so that is how the acid-base chemistry is. Acids act as differentiating solvents for acids, bases act as differentiating solvents for bases, and the other way around, they act as leveling solvents. They level the acidity and the basicity. Right? Okay, so that was about acetic acid. Now say for example, if I have ClCH2 COOH, which is called as chloroacetic acid, also called as monochloroacetic acid because there is only one chlorine, Cl2CH Cl3CCOOH. And I ask you to tell me that between these four compounds, which are the four compounds? Acetic acid, monochloroacetic acid, dichloroacetic acid and trichloroacetic acid, which is the strongest acid? Trichloroacetic acid will be the strongest acid of the lot. Why is that? Now again, since we are looking at acidity, we have to look at the stabilizing factor of the conjugate base. So the first thing you do is draw the conjugate base. Okay? Through resonance, in each of the cases you will get only two structures. Only two atoms can share the negative charge. So there is no change there. It is going to look exactly like this, except that some other substituent is going to be present over here. But having said that, each of these chlorines act as negative inductive groups, minus I groups. Okay? Because they are minus I groups, they tend to withdraw electrons from these anions, which are conjugate bases. The more there are such kind of electron withdrawing groups, the more the negative charge will be withdrawn. And like I've told you, any factor that reduces the negative charge will increase the stability. Any factor that increases the negative charge will decrease the stability. Okay? And therefore trichloroacetic acid will be the most acidic, followed by dichloroacetic acid, followed by acetic acid. Okay, now let's take another example. The same, except that I've replaced the halogen to fluorine. I could have trichloroacetic acid, tribromoacetic acid. So now what am I comparing? I'm not comparing like this. I'm comparing with different halogens. Trifluoroacidic acid, trichloroacidic acid, tribromoacidic acid, triiodoacidic acid. Which is the strongest acid? Trifluoroacidic acid will be the strongest acid amongst the lot. Why? Because fluorine has the highest value of negative inductive effect, and therefore it will be able to withdraw electrons with the greatest facility, and therefore stabilizing the conjugate base to the maximum extent.
So when the electron affinity is less in fluorine.
Yeah, but here we don't want fluorine to take up the electron completely, right, and become F minus. We are only looking at how much it can delocalize the negative charge in space. And trifluoroacidic acid is much more efficient in doing that. Okay. What about this CH3 whole thrice CCOH? It's even weaker than acetic acid itself. Why? Because the three methyl groups are pushing electrons through positive inductive effect, right? Since they are pushing electrons, they are going to increase the negative charge on the oxygen. Any increase in the charge is going to lead to destabilization, and hence the acidity is going to drop. Is that clear? So here we have accounted for just based on the inductive and field effects. What is the difference between inductive effect and field effect? Have you heard of field effects before? Inductive effects and field effects are in a sense the same, except that inductive effects operate through bonds. Okay? What do you mean by operate through bonds? If I and she are linked together with the help of a bond, I can either pull electrons or push electrons depending upon the difference in electronegativity. I call that as an inductive effect. Okay? However, in these examples, you see that chlorine is not directly attached to the carbon atom or to the oxygen atom bearing the negative charge, but is still acting as a sink of electrons. So field effects actually operate through space, do not actually operate through bonds. That's the only difference between inductive effects and field effects. But we cannot, in an isolated fashion, calculate only the inductive effect, leaving aside the field effects. We always will be able to get a value, the net value of inductive and field effects together. And therefore, we always study inductive and field effects under the same value. Okay? So whenever you are saying inductive effects, keep it in your mind that you are also simultaneously talking about field effects. Wherein chlorine, which is present in the three-dimensional space, helps in the three-dimensional structure. You can picture chlorine here and the oxygen here. So in 3 dimension, even though this chlorine and this oxygen are not directly linked, this chlorine still helps in stabilizing the negative charge on the oxygen, and hence we call that through field effects the chlorine is exhibiting. And remember that the direction is going to be the same. If it's a -I group, it is going to be -I through inductive, -I through field. It's always going to go hand in hand. The only difference is with respect to connection or through space.
So I guess we can even say that is a part of that may get it's only like active for the two carbon atoms are being there, right?
Yeah, that's right. But at the same time, even field effects will operate only when the two groups are close enough for the interaction to take place. Say for example, you have a large molecule. There is no reason why it should fold up in a particular fashion so as to bring the negative inductive group close in space with another group, right? There will be random movement of this molecule in any solvent. And therefore, as the inductive effect dies, so does the field effect as well. Unless if there is a particular conformation in which the molecule is frozen, or some geometrical constraint is put on the molecule that it has to exist in that particular form, then field effects are going to operate. Like there is a very good example. Such kind of compounds are called as helicenes, for a simple reason that this is not completely planar. It's not like 4 benzene rings lined one over the other. you will see that the first benzene ring, if it is on top, then the second benzene ring kind of slightly is at the bottom. And it is like a helix. It could be a right-handed helix or it could be a left-handed helix, and therefore we call them as helices, right? The interaction is basically stemming due to these protons which are coming very close together, and hence it displaces them from planarity, basically. Okay? So say for example, if I have a group over here which is minus I, it can exhibit a negative inductive effect on some group which is placed over here as well. But that can't be called as inductive effect, because inductive effect usually operates through bonds. So if I have a chlorine atom over here which is affecting the reactivity at this position, I'll call this as a field effect and not as an inductive. It will not become planar.
But
it is going out of planarity due to the steric reason. But the reactivity is going to be affected due to the field effect of this chlorine. Though it is very far away. If you come to look at how many bonds away this chlorine is from this one, it's massive, right? And the inductive effect is almost absolutely going to die beyond the beta carbon atom. It's not going to exhibit itself at all. But since in three-dimensional space, somehow the molecule is restricted in such a way that these two groups are coming closer together, the reactivity at this position can be affected by this, and we call them as field effects. Right? We no longer term it as inductive effect. Okay? Now, we've already looked at acetic acids and substituted acetic acids, etc. Now, what if I go from acetic acid to benzoic acid and phenol? I want you to compare the acidity of benzoic acid and phenol. Now, always remember, each time we use a different explanation to account for the acidity. But having said that, we always account for the acidity that we measure in the lab. We are not to violate that. Just because you are saying that I know of ABC rules, and according to ABC rules, phenols look like they should be more acidic. And it is actually true that based on your ABC rules, you cannot account for acidities here. You will have to bring in another rule of resonance D so as to be able to account for the true picture of acidity between the two. In the lab, when we measure the pKa values of these two compounds, for benzoic acid it comes to about 4 point something, so approximately 5. For phenol it comes to 9.8, late 9 point something, so close to about 10. So what do we already know before starting to account for acidity? That benzoic acid is how many times more acidic? 10 to the power 5 times more acidic as compared to phenol. This is what is making your separation so effective in the lab. Benzoic acid, being 10 to the power 5 times more acidic, is capable of reacting with a base which is much weaker. Sodium bicarbonate is an extremely weak base. Okay? Whereas phenol, since it has such a low amount of acidity, it's not going to be able to react with sodium bicarbonate, but it tends to react with a stronger base NaOH. Now, can you again work out this leveling solvent and differentiating solvent? NaHCO3 is a weak base, and therefore it can differentiate between the acidities of these two. When you take a strong base, bases cannot be differentiating solvents for acids. So NaOH tends to dissolve the carboxylic acid as well as the phenol. And that's why in your organic spotting we enforce that you must first check with bicarbonate and only then go ahead and check with NaOH. You can't do it the other way around. You understand that? So it is important to follow a particular order. Okay. Now, every time we look at acidity, what have I told you? We need to look at its conjugate base. For acidity, that is your fixed rule. For basicity, availability of electrons. For acidity, the stability of the conjugate base, right? What is the conjugate base in benzoic acid? The benzoate anion. I have a negative charge, single bond, double bond. So what can happen? Resonance. So there will be some delocalization. I bring these electrons here I have to push these electrons off. Why do I need to push these electrons off? Carbon will become pentavalent. Remember that under no circumstance can you have more than 8 electrons around an atom. If you bring in these 2 electrons in between oxygen and carbon, carbon will have 2 plus 2 plus 1. That is 5 bonds in all. 5 bonds account for 10 electrons. All elements till the first and the second period cannot accommodate more than 8 electrons. 2 in the s orbital and 6 in the p orbital. So 6 plus 2, 8. They do not have d orbital, so they can't accommodate more than 8 electrons, right? So it has to pack off these electrons onto the oxygen. So you get another canonical form. You call these two as canonical forms. Is there any way you can push the electrons into the ring, to the ortho position or to the para position or something?
It can be done.
Can be done?
It can be done.
How? If I bring this here, I don't have conjugation here. Okay, I take it the other way, double, single, double. Still, can you pack them off inside?
But in the other canonical structure, it could have happened.
Which other canonical
The
structure?
previous one, like what you change it like it was.
Okay, now I have it as it was in the beginning.
So if the double bond goes to the oxygen atom and the negative charge doesn't form the double bond, then there can be the resonance inside the ring.
Yeah, but then you won't account for the negative charge being delocalized, right? If you draw the structure like this and say, okay, fine, this carbon, the oxygen already has a negative charge, and say, for example, this oxygen also pulls electrons away, then the electrons will be pulled up and you will get a positive charge here. Remember that whenever we are looking at acidity and basicity, we are looking at whether the negative charge is becoming delocalized or not. What does delocalization of negative charge mean? The negative charge does not tend to remain on the same atom, but it tends to be shared by multiple atoms. That is why we say greater the number of resonating structures, more stable the hybrid will be. Why do we say that? Because more the number of resonating structures you can draw, more there is sharing of the negative charge between multiple atoms. But here in this case, as soon as you do this, you have generated a new charge, and at the same time the negative charge continues to remain localized. So it's not stabilizing. There is no stabilizing phenomena that is taking place, right? So how many resonating structures in all could you get accounting for the stability of the conjugate base? Again, just 2. Just like acetic acid, even benzoic acid gives us only 2 resonating structures for its conjugate base, right? But now when you look at phenol, the conjugate base of phenol is phenoxide, right? Is this stabilized through resonance? Yes, it is. Why? Because I have a negative charge, single bond, double bond, single bond, double bond, single bond, double bond, single bond. That means there is extensive conjugation. There has to be resonance. These electrons come in between carbon and oxygen, packing off these electrons onto one of the carbon atom. It is a requirement, otherwise this carbon would have become pentavalent. So you get the first canonical structure where the negative charge goes to the carbon atom at the ortho position. Then you bring this negative charge in between these 2 atoms. These electrons are packed off. The electrons move to the para position. So you get a negative charge here. I've already drawn 3 resonating structures. I have 2 more at hand. Bring these electrons further. What happens? The negative charge moves to the next ortho position, and the negative charge comes back. What is our concept so far? Greater the number of resonating structures, more stable is the hybrid. So, if I have only 2 resonating structures for the carboxylate anion, and if I have 5 resonating structures for the phenoxide ion, it looks like the phenoxide ion should be more stable as compared to the carboxylate anion, right? But what is our experimental observation? The carboxylic acid is almost 10 to the power 5 times more acidic as compared to the phenol, right? How do you account for this now? That's why I said we need to add more rules. Okay, we cannot be very rigid with our rules because we can't violate what we observe in the lab. Tomorrow, just because you want phenol to be more acidic, it's not going to happen like that in the lab, right? Carboxylic acid is going to continue to remain more acidic. So what was the rule that was brought up? More the number of equivalent resonating structures, that's why the term resonance. Equivalent resonating structures have a stabilizing effect that is more than the sum of the two. If you have sum of two unequal resonating structures and two equivalent resonating structures, their effect at stabilizing is many-fold greater. Here in these two carboxylate anions, you see that both these structures are absolutely equivalent. The number of bonds are exactly the same and the atom bearing the negative charge are also exactly the same. So you get two absolutely equivalent resonating structures. Here, the first and the last structures are equivalent, but structures 2, 3 and 4 are not equivalent to 1 and 4. Why? Because in structures 2, 3 and 4, the atom bearing the negative charge is a carbon, whereas in structures 1 and 5, the atom bearing the negative charge is an oxygen. And hence structures 1 and 4 are more stable as compared to structures 2, 3 and 4. So all these 5 are not equivalent to one another. And that is why this is leading to a much greater stabilizing effect to the conjugate base. Now any theory before it's put forth, then it needs to be validated. What do you mean by validated? Sirf ek case milega, so you can't propose it as a rule, right? You need to check this with multiple things. So there was one more thing. I'll close with this. This is benzene sulfonic acid. Okay? C6H5SO3H. Can you guess, just take a wild guess of the pKa value for benzene sulfonic acid? 1, 2, 3. 2 to 3. The pKa value was -7. -7. You added one resonating structure, it gave you an increase in acidity by a factor of 10 to the power 5. You add one more, it adds up by 10 to the power 13, 7 plus 5. So our theory actually holds. If you have equivalent, now today when you go back, draw the resonating structure for the sulfonate anion. What you will see is that rather than getting 2, you will get 3 structures. All of them will be absolutely equivalent to one another. C6H5, S, double bond O, single bond O, single bond O, right? Double bond O, H. So there is a negative charge here. SO3H, but its conjugate base will have a negative charge, right? I bring in the negative charge inside. So I will need to pack off one of the electrons onto another oxygen. So basically, just by looking at the structure, you can make out that all 3 oxygen atoms in one of the resonating structure will get a negative charge. So if this one gets a negative charge in the first one, the second one I can make this one get the negative charge, in the third one I can make this one get the negative charge. All 3 structures will be absolutely equivalent. And what is the cumulative effect of all 3 of them? The cumulative effect is manifold. Stabilizes the conjugate base to such an extent that the acidity of the acid goes up many fold. Right? So far we've not discussed, we've just started with discussing stabilizing the stability of the conjugate base based on resonance. But there are many different factors. What are they? You could stabilize the conjugate base through resonance. You could stabilize the conjugate base through hyperconjugation. Okay. You could stabilize the conjugate base. Of course, hyperconjugation is not very important when it comes to conjugate bases because there will be a negative charge. No, in hyperconjugation you actually stabilize a positively charged center. Usually you don't stabilize a negative charge, right? The CH sigma bond is involved in stabilization. We'll come to hyperconjugation. Huh? This is resonance. Then it's an equivalent resonating structure. Resonating structures are also called as canonical forms. So if the three canonical forms have the same energy, then they are called as equivalent canonical forms. So their resultant will be many-fold greater than having many more canonical forms but of different energies. Okay? You could also have account for stability based on aromaticity. This is one of the most important. We will come to this next time. So that because in multiple cases you are given different carbocyclic rings and you are asked to account for acidity. Like if I give you cyclopentadiene and cycloheptatriene, and I label the proton for you and ask you which of the two should be more acidic. Again, our concept is the same. When you are looking at acidity, you have to look at the conjugate base. When the conjugate base of cyclopentadiene is formed, you get the cyclopentadienyl anion. Cyclopentadienyl anion is aromatic. It is cyclic, it's planar, it's conjugated, and it follows the Huckel's rule of aromaticity, which is 4n plus 2. I'm rushing through this, but we will again be doing it any which ways next time. But when it comes to the conjugate base of cycloheptatriene, you get cycloheptatrienyl anion. This particular compound is also cyclic, planar, and conjugated, but it is anti-aromatic. There are three different types, right? Aromatic, non-aromatic, and anti-aromatic. Why is this anti-aromatic? 2, 4, 6, and 8 electrons. 8 electrons follow the 4n rule. 4n is equal to 8, so n is equal to 2. So you're getting a whole number, right? It's not following the 4n plus 2 pi electrons rule, it is following the 4n pi electron rule. So it is anti-aromatic. What is the stability order? Aromatic most stable, non-aromatic as stable as its acyclic analog, anti-aromatic even less stable than the acyclic analog. Okay, so that means between the two of them, which one should be more acidic? Should cyclopentadiene should be more acidic. Why should cyclopentadiene be more acidic? The anion that is formed after deprotonation is aromatic, which is more stable than the anion that is formed on deprotonation of this. So the pKa values will also reflect accordingly. Whose pKa value is going to be larger? Yeah, the one for the anti-aromatic is going to be much larger.
So if you have the maximum number of charges on a similar form of atoms, so we describe them as equivalent resonance structures. Equivalent resonance, right? But in looking at the acidity, we basically look at how stable or unstable is the conjugate base.
Right.
So in the case of equivalent resonance structures, if we are saying that the acidity is many-fold, which means that the stability of these bases must be very low.
Very high.
Very high.
Stability is very high. Stability is high or basicity is low. Basicity means what? Its tendency to accept the proton. That will be low provided it is stable in its anionic form. If it is anionic form, it is stable, it will not want to take up the proton and go back to the acid. So basicity will be low of the conjugate base or its stability will be extremely high. Yes. So whenever you are accounting for acidity, remember we always account only for the stability of the conjugate base. Once you have accounted for order of stability of conjugate base, you are finished. Your job is done. You can account for acidity. Is that clear? So we'll take up acidity more next week. We'll finish acidity and then we will move on to some other concept. Okay?